Hello and welcome to Physics Tips for Cambridge Students YouTube channel. And this is my second video on deformation of solids. Today we are specifically looking at elastic and plastic behavior of solids. Remember to subscribe to the Physics Tips for Cambridge Students YouTube channel. Hit the notification bell icon so that you get alerted of my future videos. Without much further ado, please let's get started. Like the lesson outcomes from the syllabus, you should be able to understand and use the terms elastic deformation and plastic deformation. Understand that the area under the force extension graph represents the work done, and determine the elastic potential energy of a material deformed within its limit of proportionality from the area under the force extension graph. Recall and use elastic potential energy is equal to half Fx, which is half kx squared for a material deformed within its limit of proportionality. Elastic and plastic deformation. So on the stress strain graph, we do have this, so stress versus strain, and we have a straight line graph from the origin until we get to P, which is the limit of proportionality. And then slightly above P, we've got the elastic limit. Please note that these 2 points are not the same. So Hooke's law is obeyed within the limit of proportionality. The proportional limit is the maximum load or tension in the wire when the extension is proportional to the load. The gradient in this section equals the Young modulus. So when we are finding Young modulus, as from the previous video, we are considering the proportionality part here. Now the line curves beyond P and continues past the elastic limit to the yield point Y1. The elastic limit is the maximum load or tension which the wire can experience and still regain its original shape and size after the load has been removed. Beyond the elastic limit, the wire is permanently stretched and suffers plastic deformation. An elastic change means that the spring returns to its original length, shape, or size when the load is removed. There is no permanent deformation. Please note that also elastic does not mean that this extension is proportional to the load. It just means that you can regain the shape, the size, etc. when the load has been removed. Yield point Y1 is where the wire weakens temporarily. Beyond Y2, a small increase in stress causes a large increase in the strain as the wire undergoes plastic deformation. So plastic deformation starts after the elastic limit. So all this is plastic deformation. Now the maximum stress which can be applied is called the ultimate tensile stress. Beyond the UTS, the wire loses its strength, extends and becomes narrower, so necking occurs until it breaks at B. So B is actually called the breaking point, and the stress that is required for breaking is called the breaking stress. Stress strain curves for different materials. A brittle material tends to have just elastic deformation. Beyond the elastic limit, it breaks. Little to no plastic deformation. Then copper, on the other hand, it is ductile, which means it can be drawn into a wire. So it has got a large amount of plastic deformation. A ductile material can be drawn into a wire, and copper is more ductile than steel. Steel, on the other hand, is stronger. So if you can look at the graphs here, the gradient gives you the Young modulus, stress over strain, remember. The steeper the gradient, the more the Young modulus, and also the stiffer the material is. So steel is stiffer than copper. The gradient is greater. Elastic potential energy. This is the area under the graph within the elastic limit that we consider here. So the work done is stored as elastic potential energy in the material. Strain energy is the ability of an object to do work as a result of the change of shape of the object. Molecules in the material gain molecular potential energy due to their displacement from the mean positions by the force. Provided the elastic limit has not been exceeded, the energy stored can be recovered. Elastic potential energy is just equal to half F times E, which is half Ke squared. energy stored per unit volume. So if you plot a graph of stress versus strain, what you get is the energy per unit volume and not the energy, please. So to get the potential energy, we plot F versus E. So stress versus strain gives you the energy per unit volume. Let's look at the examples here. Light spring of unextended length 14.2 centimeters is suspended vertically from a fixed point as illustrated there. There we are. The mass of weight 3.8 newtons is hung from the end of the spring as shown in figure 4.2. The length of the spring is now 16.3 centimeters. An additional force F then extends the spring so that its length becomes 17.8 centimeters as shown. The spring obeys Hooke's law and elastic limit of the spring is not exceeded. Show that the spring constant of the spring is 1.8 newtons per centimeter. To get the spring constant is simple. It's just F over E, and our F is 3.8. The extension between 16.3 and 14.2 is 2.1. So it's just going to be 3.8 over 2.1, which is going to give you 1.8 newtons per centimeter, as shown. For part 2, it says for the extension of the spring from a length of 16.3 to 17.8 centimeters, calculate the change in the gravitational potential energy of the mass of the spring. Now, to find the change in the gravitational potential energy, delta EP is just going to be equal to mg delta H. And we are given that the weight is 3.8, so mg is 3.8 multiplied by delta H. And delta H would be from the 17.8 minus 16.3, this is times 10 to the power of minus 2. So if you do the maths well, you're going to get 0.057 joules. The question goes on to say, show that the change in elastic potential energy of the spring is 0.077. To find the change in the elastic potential energy, it's going to be half Ke squared. And we have found K already, but then remember, K is in centimeter, so we need to change it to per meter. It's going to be equal to half times the 1.8 that we calculated earlier on, but now we're saying times 10 to the power of positive 2 because we're converting to per meter. So multiplied by the change there, so it's going to be 0.036 squared minus 0.021 squared. Because what we're going to have there is the difference between the two, that is 17.8 and 16.3, and then the difference between the 16.3 and 14.2. So Ke squared, so that's what we have there. This is going to give you 0.077 joules. Then part 3 says determine the work done by force F. The work done is just going to be the difference between the 0 point, so this is 0.077 joules. So the difference between this one and this one is going to be the work that's going to be done by the force F, which is 0.020 joules. I'm going to work out one more example and then we come to the end of the video. So in this one, it says a vertical steel wire of length 0.80 meters and radius 1 millimeter is gradually loaded with a mass of 20 kgs applied to its lower end. Assuming that the proportional limit is not exceeded, calculate the extension. We are given the length, we're given the radius, we're given the weight. We know that extension is equal to FL over AE. From our Young modulus formula earlier on in the previous video, let's just take you back there. Previous video, we said that Young modulus is equal to FL naught over AE. So AE is the extension here. So we're just making E the subject. So Young modulus just comes on the denominator. That's what we have. Since we know the weight, we know L, we know A, and we know E. So F will be 20 times 10. This is times L, which is the 0.80. over the area, that is pi r squared. Pi times 1 times 10 to the power of minus 3 squared. And then this is times the Young modulus, which is 2 times 10 to the power 11. If you do the maths well, you're just going to get 0.255 times 10 to the power of minus 3 meters. In other words, 0.255 millimeters. Then B says the energy stored in the wire, energy stored is just equal to half Fe. And this is equal to half. F is 20 kgs times 10 to convert to newtons. Then multiply by what we found earlier on, that 0.255 times 10 to the power of minus 3. If you do the maths there, you're just going to get 25.5 times 10 to the power of minus 3 joules, 25.5 millijoules. Then part C says that the loss in gravitational potential energy of the mass during loading account for the difference between B and C. The loss in gravitational potential energy is equal to mg delta H. So delta EP is equal to mg delta H. So our M is 20, our G is 10, and then our delta H is just the extension, which is equal to 0.255 times 10 to the power of minus 3, which is going to give you 51 times 10 to the power of minus 3 joules. Then they say account for the difference between B and C. So on B, you can see that there's 25.5 times 10 to the power of minus 3. And then C, we've got 51 times 10 to the power of minus 3. So the energy stored is half the loss. As you can see, this times 2, you get that. So the energy that's going to be stored is half the loss in gravitational potential energy. The energy stored is the molecular energy gained by the wire. The remainder is the energy dissipated as heat, and the wire as the weight loses its kinetic energy after falling and comes to rest. If the load is suddenly applied, the extension would be twice the equilibrium extension obtained in the question above there. So I think I'll end the video here. Remember to subscribe to the channel. Right, like, share, and comment as well. It's hitting the notification bell. Signing out.